Well, good morning and welcome to Psych 9A, Psych 11A, Psychology Fundamentals, Winter Quarter 2014. I'm going to talk today about some research that I've done here at UC Irvine concerning communication and control using brainwaves. But before I start in, I need to know, do you have any questions that I can answer? And it's a simple matter of raising your hand and saying, hey, what about this? Anybody have any questions? I take that to be a big no. You can always send email. So what I'm going to do today then is launch right into our lecture. And, oh, I must have missed your hand. I'm sorry.
You said email. Can we also post questions on your message?
I do not have a message board. I do not know how they work, and so that would not be the way to go.
Okay.
I would definitely send an email. Good question. Okay. So let me see if I can advance a slide here. There we go. The work I'm going to describe is actually the work performed by a number of people being supported by the Army Research Office. And we were awarded a contract for multi-university research, and so that's a Muri Award. And there are 3 campuses represented. There's work here at UC Irvine, there's work at Carnegie Mellon, and work at New York University. And this work is just about complete. Our contract will end in June. So let's see. Here at UC Irvine, you may recognize some of these people. So, for instance, my close colleague Ramesh Srinivasan is an expert on human EEG, electroencephalography, and he's also the chair of the Department of Cognitive Sciences. This is Greg Hickok, a well-known neurolinguist and cognitive neuroscientist who's done a lot of studies of how we perceive and produce language. And here is Karosh Saberi, who is now our Associate Dean of Research and Graduate Studies, who has a large body of expertise, including hearing and cognitive neuroscience, how the brain works and things like that. Now at Carnegie Mellon, we have experts in signal processing, and finally at New York University, this fellow David Popple is a well-known expert in neurolinguistics, namely how the brain helps us speak and understand language. So in addition to these professors, there's a small army of postdoc type people and graduate students helping with the research. And I will be pointing out some of these people as the slides progress. So you have to be asking yourself, well, what's it all about? The long-term applied goal is to use thought to communicate and control through what is known as a brain-computer interface, or BCI. So, for instance, if you had an EEG, which I'll describe, on your head measuring your brain waves, well, you might use a computer to analyze those brain waves and perhaps get your person who's wearing the EEG to be able to signal something using the brain waves, communication and control. So what we're supported for is basic scientific research, and people make a distinction between basic research and applied research. For example, basic research is the sort of thing that gets published in peer-reviewed journals, many of which to date are inaccessible to the public because they're so darn expensive. They're read primarily by other scientists. They get talked about at scientific conferences, things like that. Applied research, you'll see a lot more of that done by, say, corporate research teams. And in this particular area, you might envision a company that is trying to use EEG to help people play games, computer games or something like that. That would be applied research. Let's see. So our research involves what is known as non-invasive brain imaging. Now, non-invasive brain imaging means we would like to know what the brain is doing without actually tampering with the head. So, when you measure things, for instance, using electroencephalography, what you're doing is passively measuring changes in the brain's electrical activity. without actually putting anything into the brain or harming the person who's generating those brain waves. So that is a sort of passive, non-invasive way to figure out what's going on in the brain. Other methods of that sort are functional magnetic resonance imaging, fMRI, and magnetoencephalography, which is a non-invasive way to measure the magnetic activity generated by the brain as it works. And we are going to go over this sort of thing in detail once we hit chapter 3 in our textbook, but I can tell you that there are also invasive methods for studying brain activity. One of the oldest ones is to remove a little piece of skull and then to have a very thin needle-like electrode measure the activity of neurons that it touches at its tip. So that would be an invasive method because you've removed part of a person's skull. We're not doing that kind of thing. Now, there are two axes in this research. One of them is the brain imaging using the non-invasive methods, and the second is signal processing because these devices are producing lots and lots of numbers concerning brain activity that must be interpreted if we are to make sense of what the brain is doing. And so the signals that they provide must be processed by a computer. And so we need signal processing methods. So that's the two sorts of things. Now, as for EEG, which has been my focus, well, the first EEG recordings of human brain electrical activity were by this fellow Hans Berger way back in the 1920s. And here we have a picture of a former graduate student named Sam Thorpe here at UCI wearing an EEG cap. And it looks sort of like a swim cap, you know, like the water polo team. And that's really what it is, except in addition to having the water polo cap, they've got these little things there, and those are called electrodes. And that is actually what is going to be doing the measurement of the brain electrical activity, these little electrodes. And they're sitting on the scalp, and they're held in place using that cap. Now, you might be wondering how many of those little electrodes there are. And it turns out you can buy EEG systems that have 256 electrodes scattered across the surface of the scalp. And so this cap is literally dotted with millions of little electrodes. Well, 256. And we have some systems with that number of electrodes here on campus. We have some with 128. I tend to work with systems that have 64 electrodes, but they're also 32, 16, basically power of 2. You will find your EEG system. So, electrical activity is reported at each one of these electrodes at a very high rate. So you might have 1,000 measurements of electric field potential per second. So, what does that mean? It means you're getting a lot of data. If you have, say, 128 electrodes, and each one is giving 1,000 pieces of data per second, well, that would be 128,000 data per second from the entire head. And you can now begin to see, well, you probably need a computer to crunch the numbers to keep up with that flood of data. And that's exactly where all this signal processing comes in. Now, EEG activity, in electroencephalographic activity, is often described in terms of activity in certain frequency ranges. And these ranges have traditional Greek letter names. And let's see, we've got delta waves, and these are very slow waves. And you might have 1 delta wave per second or maybe 2 delta waves per second. But in effect, you're getting a very small number of waves every second. And if you have an electrode that is, say, positioned right here in the front top of the head and a person is deeply asleep, you will measure these very slow waves, delta waves. We'll talk about that later in the course. Now, let's say a person is meditating, or again, you have an electrode that's sort of towards the front of the head. Well, you can, in this awake person, you will then be able to measure waves that are going up and down in electric field potential more rapidly, say 4 times a second or even up through 8 times a second. Alpha waves are faster. You're going to get approximately 10 of these every second. And these are very interesting. people rely on alpha waves very strongly in work with brain-computer interfaces. One of the things they do is signal whether a person is aroused and awake or relaxed or just sort of like chilling out with their eyes closed. If a person is relaxed or has their eyes closed, then there will be a lot of alpha rhythm activity. And you'll find very big waves, maybe 10 of these per second. If a person is alert and aroused and they're running around doing things, then the amplitude or size of these waves will be much smaller. That's the principle. Beta is even faster, 12 through 28 hertz. Now, Hz is effectively a unit of frequency, and it says how many waves you get per second. And it's named after a German physicist named Hertz. I guess you'd say Hertz auf Deutsch, but Hertz is how I say it, Hz. And that means 12 to 28 hertz. Well, beta waves are in the range of 12 waves per second through 28 waves per second. And finally, gamma. These are very, very fast waves, and they're thought to be related most strongly to the activity of muscles in the head. And I'm talking about muscles at the temples, or scrunching your eyeball type of muscles, or your neck muscles. That can generate gamma wave activity when you're recording EEG. So, this is the sort of thing you see with EEG. I think what's most interesting is that EEG is not giving you a direct picture of what's going on in the brain. Rather, it's giving you a picture of brain activity seen through a very thick wall. And what thick wall am I talking about? The skull. The skull is effectively a thick wall, and you have all of these neurons in the brain behind the wall, and they're doing this, they're doing that, they're helping you think, they're helping you run around. And they're shouting as they do their business, but you're not going to hear that shouting very much using EEG, because those changes in electrical activity have to get through the skull before they actually reach an electrode that's lying on top of the scalp. So it's like somebody is outside that wall there shouting, and we're trying to hear them using a stethoscope. We're not going to hear very much. It's going to be a little bit dubious. And in fact, if you have just one person outside that wall there shouting, we're probably going to hear nothing. What we need is a large number of people outside the building shouting. Then we'll hear them. And that's the principle of EEG. What we are recording with EEG is the activity of large numbers of neurons simultaneously doing the same thing in terms of electrical activity. And so it's really important that you have a large number of neurons acting in a synchronous fashion, acting together so that we hear them in some sense using our EEG electrodes. So we're getting this very gross or coarse or large-scale activity measured using electroencephalography. And that's very different from invasive measurements. I mentioned a moment ago, you can remove a piece of skull and then put this really thin needle in and start recording from individual little areas of the brain. Well, there you'll get a very detailed measurement of brain activity in the location of the needle's tip. Here, it's almost the opposite. We're getting this very sort of coarse measurement of brain activity that's spread out over a wide area because we need a large number of neurons, which occupy a wide area, to effectively work together to give us something we can measure. So, brain-computer interfaces. People have been working on this for a while. So here's 1964, this fellow named Dewin trained himself to start and stop his EEG recorded alpha rhythms. And one easy way to do that is to simply open your eyes and you'll have less alpha, and then close your eyes. You'll have more alpha. But he trained himself to do this without opening and closing his eyes, simply by relaxing and getting more aroused. And he was able to do this so well that he could transmit letters using Morse code. So the amount of alpha waves effectively was going up and down, and he was able to do this so well he could send Morse code to say individual letters. So this is really the first example of a brain-computer interface that I'm aware of. This guy signaling letters using Morse code by modulating the strength of the alpha rhythms. And now you have to ask yourself the question, can we use brainwaves to signal linguistic content more directly by using imagined speech? What is imagined speech? Well, when I read, I actually have a little voice in my head that I hear when I read. And if I'm reading very quickly, it's sort of going, but if I read slowly, then I can hear each individual word, typically in my voice, more or less clearly. When I am thinking to myself, sometimes I think really quickly, or sometimes it's all in pictures or something, but there are other times when I actually say the words clearly to myself. I hear the voice in my head. That's what I'm talking about with imagined speech. And now the question is, well, that must correspond to some kind of brain activity. It's not coming from nowhere. Our brain is helping us imagine speech. Is it the case that we can use EEG to detect this imagined speech brain activity and decode it to figure out what a person is saying to him or herself? So that's sort of fun, huh? Let's see. Now, Greg Hickok and members of his laboratory have sort of formulated a model to help us think about this speech production issue. And the thing to bear in mind is when you are imagining speech, there are two kinds of imagery that you might want to detect using EEG. The first kind is what you hear in your head. I have this little voice in my head when I imagine speech. It's my voice, but it's definitely inside my head, and I hear it. It's not the same as hearing your voice when you talk to me, but it's fainter. It's inside my head. I'm still hearing something. That's known as auditory imagery. So when you imagine speech, there is auditory imagery. Another thing there is, and this can be more or less emphasized, there is motor imagery. When I imagine speech, I can imagine speaking clearly with a lot of good enunciation, and in that case, there is motor imagery. I sort of have this picture in my mind, it's sort of hard to describe, of how my mouth is moving, or would move, I should say, how my mouth would move to generate the words that I am thinking. That's known as motor imagery. So how does this imagery get created? And the idea is that there is a feedback circuit in the brain that is used when we speak out loud, and it effectively feeds back a signal that is always generating effectively a prediction of what your speech should sound like, and a prediction of what's going on with the way you form the words with your vocal tract. This same kind of feedback is generated when you imagine speech and gives rise to auditory imagery and motor imagery, even if you're not saying anything out loud. So, that's sort of an overarching idea. What about particulars? Well, here is a former grad student, Dr. C.E. Dang. He actually now works at a EEG company that helps develop EEG products for games and for other things. Anyway, he showed that one can use EEG to discriminate among imagined speech streams that vary in their rhythm. Now, I want to describe this experiment in some detail. This experiment is one that has 6 conditions. So we're going to sort of compare the results from 6 conditions. And in this experiment, 2 syllables were used. 3 of the conditions used the syllable ba. The other 3 conditions used the syllable ku. So we ended up calling this the ba-ku experiment. In any event, there were 3 rhythms. And the first rhythm is illustrated here for the syllable ba. So this is one of the bas. And then you hear click, click, click. And after those 3 clicks, what you are supposed to do in your mind is say ba, ba, ba. So that's what's happening with this first condition. You hear ba, and that's saying, well, please imagine the syllable ba. Then you hear click, 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 And then your job is to keep that rhythm and say ba, ba, ba to yourself. So that is our first condition. What is our second condition? Well, it's a different rhythm, but it's the same syllable. So you hear ba, but then you have click, 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 click. And what you're supposed to think is ba, 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 ba. Sounds pretty stupid, doesn't it? It's going to be even worse now. So you hear in number 3, ba, and then you hear click, 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 click. And you're supposed to think ba, 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 ba. Now, I'm saying these things out loud, but in the experiment, you're sitting there very solemnly, not moving any muscles, and thinking it as clearly in your mind as you can. Okay, there's no messing around. You're really supposed to punch out those words in your imagination, but without making any sounds or moving any muscles. Really has to be in imagination. So those are the 3 basic rhythms illustrated with ba, and then you can do the same rhythms using ku. So this one down here would be ku, 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 ku. Ku, 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 ku. Ku, ku, ku. You got the idea. Okay, so what we want to know is, well, if we are putting an EEG cap on the person who's thinking these various things, and the EEG cap is providing signals that go into a computer, can we then use our computer to determine which of these guys, there are 6 possibilities here, which of those the person is thinking? And what CE showed is that, yes, you can use EEG to classify trials according to the rhythm with which the imagined speech is generated. So you can tell apart the first from the second from the third rhythm using EEG, which is pretty fun. What you cannot do, at least we weren't able to do it in this experiment, was to determine whether the person was thinking the ba or the ku. We could not tell apart the syllables. We could tell apart all of the rhythms, but we could not tell apart the syllables. As far as EEG was concerned, ba was the same as ku. So that's a start. So what CE did was a second experiment. Instead of using syllables ba and ku, he said, well, maybe what's going on with ba and ku is effectively it's the volume of the imagined speech that is getting transmitted through the EEG. And when you have a rhythmic utterance like ba, 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 the volume is going to go up, up, up. When you have a different rhythm like ba, 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 then your volume will go ba, 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 ba. You can effectively measure the volume, how loud the imagined speech is, well, the real speech, how loud the real speech is, and get some idea, perhaps, of what is being signaled using EEG. That's the idea. And you can then say, well, if we can do it using bas and kus, we should be able to do it using real sentences. So here's a sentence: critical equipment needs proper maintenance. And you can imagine a little volume meter that's recording how loud it is when a person says this. And that blue trace right here is effectively showing you, for a particular person, how loud the speech is at any one moment in time. The hypothesis is that the EEG is signaling, effectively, this loudness. And if we have, say, 4 or 6 sentences that all have different loudness contours, then we should be able to tell apart the sentences using EEG. Now, does that make sense? If the sentences have different loudness functions, then we can use EEG to tell them apart. And that's the way it works. That is true. He had 6 sentences and got it to work. So that's pretty neat. Now, we showed up on Through the Wormhole late last year, and I now want to switch to that video. And that video is here. Now, my only worry is that this computer does not have any volume. I'm not certain how to do this. We will see. Ding, ding, ding. Volume. Call it a brain-computer interface. We use EEG to measure the faint signals generated by the brain when a person thinks. Our goal is to analyze the EEG signals to determine what it is the person is thinking. We can then send the phrases to some other person using any number of means, including email or text messaging.
Mike is testing whether this man can use the brainwave generated.
Professor John Hagedorn teaches Psych 7, among other things.
Morse code.
There are two syllables presented as beginning of trials. These are either whoa or fit. If our subject hears fit, then he thinks fit. Fit. If he hears whoa, then he thinks whoa. Whoa. Fit could be used to communicate the short element of Morse code. Dit. Whoa can be used to communicate the long elements of Morse code. Da.
The meta Morse code tests have been stunningly successful, with an accuracy rate near 100%. This synthetic telepathy technology exploits an error correction mechanism in the brain. When the brain sends a command to the motor cortex, it also creates an internal impression known as an efference copy of what the resulting movement would look and feel like. Mike and his collaborators realized that if they could read these efference copies in the brain, synthetic telepathy could advance to the next stage, transmitting thoughts not just in Morse code, but in common phrases. Finding and isolating an efference copy in the electrical jumble of the mind is no easy thing. The exact location of neural activity is difficult to discern because the scalp, skull, and cerebral fluid surrounding the brain scatter its electric signals before they reach the electrodes of an EEG.
Hey, where's Ruth? Right here. Yeah, owner says so.
Okay. Everything back to normal. Something. Oh, I see what it is. Good. So there are two parts to this research program. One of them is to explore the transmission of imagined speech, and the basic principle that we've hit upon is to effectively try to read out the volume modulation, the change in volume as somebody says something to him or herself. The second thread in this research is to see how somebody can signal direction using EEG or some other brain imaging method. And in this intended direction research, there have been several studies and a little bit more in the way of applications. And one of the first studies we did in Professor Srinivasan's lab was done by Sam Thorpe. And here's Sam over here. You saw him earlier wearing that swim cap. Former UCI grad student Sam Thorpe conducted an experiment to see whether the direction of covert spatial attention can be decoded from EEG. Now, you have to ask yourself, what is covert spatial attention? Mark, would you say something?
So covert spatial attention is when...
Good. That's exactly what I needed right there. Basically, if somebody attracts your attention, usually what you do is you turn and look at that person. Now that is called overt orienting. You're orienting yourself to obtain the maximum information possible from that person. So your ears are facing that person, your eyes are facing that person, your body's facing blah, 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 blah. This is overt. You're now in a position to get the most attention out of things. It's also possible to direct your attention without giving any overt signal that you're doing so. So say something again. Yo. So I was paying attention to sounds, in this case speech streams coming from your direction, but I wasn't giving any clue that I was doing so. That is covert, sort of secret. People are able to direct their attention in directions without giving any outward indications that they're doing so. And they're able to do this sort of covert direction of attention to visual events. Say, I can be looking at you, even though I'm actually looking at you. So I'm paying attention to you, and you're not moving, you're not doing anything interesting, but I would see it if you would do something interesting, because I was actually paying attention in your direction rather than yours. That's covert visual attention. Much easier to understand probably is covert auditory attention, and that's when I'm looking over here, he says something, and I'm ready for it, because that was paying attention to auditory events over in that direction. We do that all the time. So, here's a question. Let's say we have a person in an experiment. On some of the trials, they pay attention to somebody talking on that side, and on some of the other trials, they're paying attention to somebody talking on that side. Simple question. Can we use EEG to figure out which side the person was paying attention to? This speaker or that speaker? And that's Sam's experiment. And of course, I wouldn't be talking about this unless the answer were yes. And in particular, what you find is that there are certain regions of the brain that give rise to strong signals that can be used to tell whether the person is paying attention to the left or the right. And in particular, there are regions in parietal cortex, which is strongly implicated in the direction of attention in previous work, where you will find electrodes that are very informative about where a person is listening. And furthermore, if you pay attention to what's going on in the alpha rhythm band, which you'll recall was in the 8 to 12 hertz range, you will perhaps obtain the maximum information about the direction in which a person is paying attention. So it turns out that this result, which was done with speech coming out of either a left speaker or a right speaker, is very similar to what people have found with visual experiments, suggesting that the covert direction of attention works similarly for the two sensory modalities. Now, more covert spatial attention to speech stream experiments have been done by Cort Horton. Dr. Cort Horton is now a postdoc here at UC Irvine, working at the Autism Center in the med school, also working here in social sciences. So, what Cort did was an experiment on the cocktail party effect, and the idea here, if you're not familiar with it, is pretty simple. Let's say you go to a really loud party, and there's millions of people talking. There might be music too, and all sorts of other sounds. But you're there with your friend, and you would like to hear what your friend is saying. How is it that you are able to pay attention and hear what your friend is saying despite all of the other noise in the room? Well, that's the cocktail party effect. We are able to direct our attention sufficiently well, almost all the time, to hear our friend. And we want to know how that works. So what Cort did was an experiment to see whether we can use EEG to tell if there's a difference in the brain processing of attended and unattended speech streams. So the idea in this experiment is to ask a person to pay attention to the speech coming from one side. Let's say that's our friend over here. Oops, sorry. So there's talking. We're supposed to be paying attention in this direction. Meanwhile, there's this other person we're trying to ignore over on that side, and that's the unattended speech. But it turns out that, both of these speech streams reach our ears and they go up into our brain and get processed. And the real question is, well, what is the effects of paying attention to one of these speech streams and ignoring the other one? Can we see what the difference is? So Cort did some fun experiments with this sort of thing and found that the loudness envelope that you record using EEG, and remember that's the trace of the loudness of how loud speech is. EEG responses to the loudness envelope of a speech stream depend on whether the stream is attended. So if I'm paying attention to somebody over here, and then the trace of the loudness from that person's speech will be really strong in the EEG. If I'm ignoring the speaker over here, then the trace of the loudness will be really weak. It's that simple. So that is a very interesting thing. It suggests that there are lots and lots of neurons paying attention, sort of synchronizing themselves to the person that you're paying attention to, and there are very few neurons synchronizing themselves or effectively responding to the speech of the ignored speaker. So that's sort of fun. Effectively, what Cort was able to do was use the responses to speech loudness envelopes to tell whether a subject is attending to the person on the left or to the person on the right. And that's a nice result.